sit in this front desk because it's holding the camera. I don't know how Dennis does it. Okay. He also promised me he would not listen back to this lecture recording, so we can talk about whatever we want. Okay. So exercise metabolism. Well, I'm not going to say bad things about him. If he hears anything, it's going to be these first 2 minutes and be like, what is she talking about? Okay, so how many of you have like a chem, biochem background in terms of you taking a class in it? Yeah, okay. So lots of you, but not necessarily all of you. Just interrupt me if I'm glazing over things that you've not covered before. So the fuels for exercise are carbohydrates, fat, and proteins. These are obviously the things that you take in order to prepare for proteins. These are not the things that are actually metabolized by the cells, but these are the things that get broken down to be metabolized. So they provide the energy. You guys talked about ATP synthesis a few lectures ago, right? Yeah. So we know that we need to make ATP. What do we make ATP from? These guys. And that allows us to maintain cellular activities at rest and during exercise. Does this, no. Does that freak anybody out, that figure? Raise your hand if it scares you. Yeah, that's fair. Okay, so I'm going to be showing some pathways like this throughout lecture because to me, they actually make things make more sense. Okay, anyway, I'll just point. Can I use my mouse? I can't. So it's just to show, and I think it helps you to understand better how the pathways work. My whole, theory on physiology is you shouldn't be memorizing stuff as much as possible. You should be understanding it. So when you look at pathways like this, it makes it so you only have to really memorize one or two things, and the rest of it sort of makes sense. So we have here's glycolysis. Have you guys learned glycolysis in the past? Yeah, I haven't taken you through all that because I figured let's not. But we know that glycolysis is our form of anaerobic metabolism, and you can have things like glucose, for instance, come into the pathway, and you end up with pyruvate and acetyl-CoA, which I'm going to be talking about a lot today. I think I have acetyl-CoA, basically our goal with almost all of our substrates is to make acetyl-CoA, because acetyl-CoA is the thing that's going to go right into the Krebs cycle. So highlight or circle acetyl-CoA in your notes, and it'll make your life a lot easier. And the nice thing about this figure is it shows. So you start with carbohydrates, and we all know what carbohydrates are, right? Bread, sugars, yada yada. So they get all transformed down to glucose, and then through glycolysis you get pyruvate, and then acetyl-CoA. Boom, you've got acetyl-CoA. Now you can go into Krebs cycle and make all kinds of energy. What about fats and the fatty acids? So you can see that, I really wish my pointer was working. You have glycerol and the fatty acids that can go in. I think they go to glucose 6-phosphate, obviously, no need to memorize that. But then the glycerol can go to pyruvate and can go to acetyl-CoA. Bob's your uncle. The fatty acids can go right to acetyl-CoA. And we're going to talk a little bit about that later. But basically the whole goal of exercise metabolism that we're going to talk about is to get things, generalization, down to acetyl-CoA. Because acetyl-CoA, boom, into Krebs cycle, yada yada through Krebs cycle, electron transport chain. So goal, get stuff to acetyl-CoA. The proteins are different. Forget about those right now. They can enter at a few different spots. I'm going to talk about them later. I've shown you this chemical structure of acetyl-CoA. You will never be quizzed on, here's a molecule, what is this? But I might ask you what the most important, or the precursor that all the different substrates can create. It's acetyl-CoA. And you can see there's 2 carbons. Boom, boom. So the nice thing about learning the chemical structure, well, you don't have to memorize them, but seeing the chemical structures and being aware, is it tells you how many acetyl-CoAs you can make, and then it tells you how much energy you can get from something. The more acetyl-CoAs you can make from something, i.e. the more carbons you have, the more energy you can make. Does that make sense? Are the people that hated this still hating it? Are they a bit better? Are you still hate it? Yeah, that's fine, you can still hate it. Okay. We'll show this in a few different ways, so hopefully you'll love it by the end. Okay, so where do we store these? So you have a meal. You're presumably, let's say, eating all of them. So where do these things get stored? Because as you know, you can hang on to your food. You don't have to like exercise and go work out right away. So we know that the liver is a nice storage site for glycogen and deaminated amino acids. We've got the muscle tissue and our intramuscular energy stores. And then, of course, adipose tissue where we store fat. I think that's fairly obvious. Also, I brought a blazer to wear, but it is hot in here. Is anyone else really hot in here, or is it just because I'm up here at the front? I'm sorry. I'm going to be drinking a ton of water because I'm real hot already. Okay, just pretend I'm wearing a blazer. Okay. So the liver, like I said, produces a rich source, provides a rich source of amino acids and glucose. We know this about our fat cells, that they can give us the energy-rich fatty acid molecules. What do you think fatty acid molecules have a lot of, based on my previous little soliloquy? Yeah?
Carbon.
Carbon! They have so much carbon. Perfect. So there's a ton of carbon in fatty acid molecules, thus making them energy-rich. And then the bloodstream, obviously, delivers the compounds to the muscle cells. And once again, we have just another way of showing this exact same diagram. This one's obviously a little bit simplified, but you've got your amino acids, your glucose, and your free fatty acids. Again, getting to acetyl-CoA through different means, but most of them, except for some of the amino acids, are going to go to acetyl-CoA and then into Krebs, or the citric acid cycle, electron transfer chain. Okay, so we know that carbohydrates are made up of carbon, hydrogen, and oxygen. My dad was also a chemistry prof, so I get really excited about this kind of stuff. It's fun. Just maybe this is why I'm warm right now. Okay, I'm just getting excited. So glucose, did I put a picture in? I did, later on. I'll put it in. Okay, so again, don't stress out. I'm not going to quiz you on this, but this so you can see them. I wish I could point at them. Glucose is over there, that monosaccharide. Every single one of those bonds has a carbon. So chemists are a bit annoying in that they don't always say where the carbon is. They assume that if there's just a joint and they don't say what it is, that it's a carbon. But you can see that glucose has 1, 2, oh, there's an option there. 1, 2, 3, 4, 5, 6 carbons. So you could make how many acetyl-CoAs from a glucose? Yeah, 3. Okay. Disaccharides, 2 monosaccharides, you can imagine. Now we've got 12 glucose, etc. Polysaccharides containing 3 plus monosaccharides. Right, yeah, you get it. So again, the more carbons we're adding on, the more glucose molecules we're adding on, the more carbons we get. That's why people talk about why it's important to eat complex carbohydrates and why they're so good for you if you want to go exercise, because there's a lot of carbon in them. Okay, have I lost anyone? Is anyone really upset I'm teaching this lecture? Okay, if you are, don't tell me. Oh yeah, I had acetyl-CoA up there with the carbons, just to remind you. Okay, so a few important carbohydrate conversions. So glycogenesis. You guys probably know this from your previous classes, but if you ever forget what any of these are on the exam, for instance, I think the name kind of tells you the answer. So glyco, we're making glycogen. Well, glycogen. Genesis, making. I watched some of Selena's lecture from last year, and she's like, Genesis, the first book of the Bible. So if that helps you at all, I don't know, where they make. Okay, I laughed anyway, so I thought you guys would laugh at us too. So again, Genesis, making, glycogen. So glycogen synthesis from glucose in the muscle and the liver cells, catalyzed by an enzyme, glycogen synthase. I'm sure you guys have already learned that all enzymes end with ASE at the end. That's your dead giveaway, you're talking about an enzyme. I do have a favorite enzyme in the body. We won't talk about this right now. We talked about this. It's at the heart. Spoiler. Okay, gluconeogenesis. Again, we can break that down. Glucose. Neo. Anyone know what neo means? New? I heard new, right? Yeah, new. The matrix. Actually, I don't know if that's anything to do with being new. Anyway, whatever. Has anyone seen the Matrix?
Yeah.
Yeah, okay. Great movie. Genesis, again, making. So glucose synthesis from non-carbohydrate nutrients usually. So for instance, proteins to glucose. Again, if you kind of like get the gist of those pathways, you'll see if anything can go to pyruvate instead of going down to acetyl-CoA and Krebs cycle, it can boop back up to glucose, and then you get glucose. And then you can convert it to glycogen. This is a bad time to be talking about this because I don't have the pathway to show you, but you'll get it when we go back to it. So once produced, glucose can follow one of three pathways. It can become available as an energy source for metabolism, so anaerobic glycolysis. I'm going to ask you stupid questions, but just so I don't have to talk through the whole thing. What's anaerobic glycolysis? Oh, maybe it's not a stupid question. Somebody knows. What's anaerobic mean? Did you guys cover that? Oh, you're just shy? Is it because I made a student of the day stand up? You don't have to be a student of the day. Does anyone know what anaerobic means? Oh, did you guys all know that? No oxygen? Yeah, you did. Come on. Don't leave me hanging up here. I already have to put a lozenge in. Now you have to listen to me crack this around in my mouth. Okay, so no oxygen. Where was I going with this? Oh, glycolysis, obviously. So we can run that part of glycolysis that doesn't require oxygen. This is handy because that's the really fast part of energy metabolism and creating ATP, which is helpful if you want to do something fast. Are there any sprinters in the room? You guys are real quiet. Are you always like this? Yeah? Do you want me to stop asking questions? I can do that if you want. But again, I'm just going to have tons of lozenges. Actually, I'm not going to stop asking questions. All right. Thank you for answering. And so when we have anaerobic glycolysis, we end up with lactate. Anaerobic glycolysis, so with oxygen, by the way, without oxygen, with oxygen, I agree on your definition. But remember that anaerobic glycolysis will still happen when you've got oxygen on board. It doesn't mean that oxygen prohibits anaerobic glycolysis from happening. It just means that oxygen is not required for it to keep on functioning. Pretty cool? Okay. But you require oxygen to go through aerobic glycolysis. Okay, where was I going with this? Oh yeah, glucose can also form glycogen. I'll talk about that in a slide or two. For storage, for future use, handy. Or we can actually convert glucose to fat for later use as energy. If you're like me, you don't exercise a lot, eat a lot of glucose, get a lot more fat. All right, glycogenolysis. Does anyone know what lysis means? You can just yell it out. I saw a lot of this. That's right, good. So breaking apart of glycogen. So you've stored your glucose as glycogen when you've got extra energy. Yeah, that's cool. Just don't sit in this one. Okay. And so now you can use it as energy later on by producing glucose. So let's say you're an average 80 kilogram man. Where's all your carbohydrates stored? So most of it you can see is stored as muscle glycogen. So handy that it's in the muscle, so it's right there ready to be used for your metabolism. The second most is in the liver, stored as liver glycogen, which again is ready to be released should it be needed. And then just a little bit circulating as plasma glucose. Okay, I find this super annoying, so I'm sorry if this is really setting anybody off. I'll try not to do this much. Okay, so carbohydrates provide the only macronutrient substance whose energy generates ATP without oxygen, anaerobically. Gave away the answer. So in order to metabolize fats and proteins, again, we're not really like going for that, but fat, you need oxygen on board. So carbohydrates are, again, the only place where we can get our energy without oxygen, which is particularly important in activities requiring rapid energy release above those levels supplied by aerobic metabolism. So again, for all the sprinters out there, or people who do sprint sport. I played hockey last night, real out of shape, and probably didn't carbohydrate load as I should have, and was just gassed. I almost puked. It was bad. If you know anyone that plays in staff hockey team, you know, it's pretty embarrassing. Okay, so in such a case, intramuscular glycogen would supply most of the energy for ATP resynthesis. So again, if you need glucose and you need it fast, that's why the glycogen is handily stored in the muscle, so it's ready for action. Okay, and then a fun fact, that aerobic breakdown of carbohydrates occurs more rapidly than fatty acids. So, again, who is scared by what I have on the right-hand side? You can be honest, yeah? Okay, again, you don't have to memorize any of this. Honestly, if you made me fill that out, I would get like, maybe like 2 out of whatever there are on here. But what I wanted to point out, again, my pointer would be really nice here. So you've got glucose going to glucose 6-phosphate. I feel like you guys have done carbon glycolysis, right, at some point? Yeah? Okay. Glucose to glucose 6-phosphate. So I feel like this is the step that everyone can remember. At least I always remember this step. So glycogen, this is where glycogen comes down. So when you break down glycogen, we're not making you memorize the chemical makeup of glycogen, the chemical makeup of glucose, and all that kind of thing. But as soon as we break down glycogen, we end up with glucose 6-phosphate. So we're one step down glycolysis, so we're moving fast. And again, all of this is just to say yada yada yada, things are happening, blah 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 blah. Pyruvate, and what comes after pyruvate? Noise. Okay. Acetyl-CoA. So again, in the presence of oxygen, we're carrying on with things, we're going to acetyl-CoA. When do you get lactate? Did you guys cover this last class? No. Yeah, you did. When do you get lactate? Yeah. Well, yeah, sorry. So like, what kind of an activity would you be doing? Let's say an aerobic. Yeah, thank you. Sorry, I was really leading with that question. That was bad question. So you're going to have pyruvate going to an acetyl-CoA as long as you don't have a backlog. Because the thing about oxygen, I really want that full diagram up in the background. As long as you got oxygen chugging away in the background, your ETC is running. So that means that your Krebs cycle is running. It's all like a big machinery where things are making other things move. If you have no oxygen on board or a deficiency of oxygen, then you're going to stop your electron transport chain. You can't do your electron transport chain. Well, the products of Krebs cycle are going into the electron transport chain. So now you've stopped that. So then what are you going to do with all that pyruvate? It can't go anywhere. We're stuck. So it goes into lactate. And I know who here hates lactate? Okay, good. Nice, good. I once did a sprint interval training study and I was dying and I was lying on the floor. I'm really out of shape, guys. So I'm lying on the floor like in grad school. One of the guys is standing over me. He's like, "Get it up! You're gonna have lactic acid in your muscles." But little did he know that it was just gonna be stored for later and I can use it later for energy. He was really mean to me, and I did throw up that day. Really bad. Okay, so where was I here? Yeah, again, ignore those enzymes, frankly. It was just part of the diagram that I picked. But I wanted to show you, the thing I liked about this up top was this glycogen. It helps you to know where the glycogen goes in, because then you can tell, if someone asks you the question, can glycogen be utilized under anaerobic conditions, what would your answer be? Who thinks yes? Who thinks no? Who has no idea? Who's just not volunteering? You guys all should big hands. Okay. So glycogen can be used under anaerobic conditions because it's coming in right at the top there when we're still creating energy without having to go past pyruvate. Does anyone want me to go back and re-explain something? Okay, I shall carry on. I'm just going to assume everything's cool, which is probably not great. So maybe when we get to the next summary slide that has all the pathways, we'll pause and you guys can ask me any questions. I'll have to stop you guys from asking too many because you're so chatty. That was sarcasm, sorry. Sarcastic teachers aren't good. Okay. So fat, like carbohydrates, fat are made up of carbon, hydrogen, and oxygen atoms. However, the ratio of carbon to oxygen is higher in fats versus carbohydrates. So we've got palmitic acid up there with 16 carbons. Does anyone remember how many carbons are on glucose? Nice. Ooh, sarcasm works on you guys. Okay, good. 6. So obviously, for one molecule of palmitic acid, we can create a lot more energy, a lot more acetyl-CoA, a lot more energy than with one molecule of glucose. So as you guys probably know, fat gets stored on the body fairly easily in my case. So fat is stored primarily within the adipocytes as triacylglycerol. Oh yeah, I skipped over this part of the past slide, but you get 4 kcals for glucose, or so for 1 gram. 1 gram? You can see it in your notes. Don't quote me on this. I don't know the answer. And then in fat, 1 gram of fat, 9 kcals of energy. If we go back to our 80 kilogram man, where are the fats stored? This is probably not surprising. It's mostly in adipose tissue. A little bit as intramuscular triacylglycerols, and then even less as plasma-free fatty acids, that's FFA there, and plasma triacylglycerols. So hopefully you don't have too much fat circulating in your blood. Any questions while I take a sip of water? Onward. Did anything happen? Oh yeah, I put my acetyl-CoA over the top again. Basically, think about how many acetyl-CoAs you can make from fat. So if I ask you, you've got a molecule of carbohydrate, you've got a molecule of fat, which one's going to create the more energy? Unless, unless. So that will be the answer if it was glucose versus fat. But there might be some complex carbohydrates that have just like a ton of carbons on them. I know, trick question, I'm sorry. And you guys even participate. That's really nice. So glucose, yes. So basically if I asked you that question, you'd be like, you need to give me a lot more details. What are we talking about? What's the chemical makeup of our carbohydrate? Stop trickiness. I won't trick you on the exam. Okay. So fatty acids are the primary type of fat used by cells for ATP production, as we talked about before. Stored, we've already said all this, in adipocytes as triacylglycerols. Lipolysis, I think again makes sense. We got lipo meaning fat, lysis meaning breakdown, process of breaking down triacylglycerol into fatty acid and glycerol, which is catalyzed by lipase enzymes such as hormone-sensitive lipase. So fatty acids then go to acetyl-CoA, this is not even my slide, this is Dennis' slide, via beta oxidation. Do you guys know what beta oxidation is? I mean, I've kind of told you. You got like glycolysis for your carbohydrates, beta oxidation for your fats. Thanks, Chris. He's nodding along up here. Okay. And then those can go into Krebs cycle. I think I have a figure to show you that later on. And then liver gluconeogenesis converts glycerol to glucose for use in anaerobic glycolysis and aerobic glycolysis. As you can see, all of this over on the right-hand side. So your fats, triacylglycerol stored in your adipose tissue. Have you guys ever seen those things that people have in their labs that's like the 1 kilogram of fat and just sits there? Have you ever seen those? Crabs always have those in their office. That's such a bummer. Alright, anyway, that's just a sidebar. Hormone-sensitive lipase will break that apart into fatty acids and glycerol. Why is it important to know that they break them apart into fatty acids and glycerol? I think I have a slide later that shows all this. It's one of my nice pathway slides. But glycerol goes into glucose. And so it can be used for anaerobic glycolysis. The fatty acids get converted to free fatty acids, and they get converted separately to acetyl-CoA in a process that requires oxygen. So the glycerol part and the free fatty acids get broken apart by these hormones, and then they go through separate pathways. Cool. Again, this is something you don't have to memorize. Don't freak out. But I wanted to show this because I'm obsessed with showing you carbons today for some reason. So here we have an unsaturated fatty acid. Up at the top, you've got that glycerol. Oh, I'm showing you on my screen. The glycerol molecule up here. Here are the fatty acids. Each fatty acid, you can see, just has a ton of carbons. Ignore the stuff at the bottom, but the double bonds. You can read more about that in your textbook if you're really into like nutrition, unsaturated versus saturated fatty acids. Sorry, past travel, it's funny, putting in all these acetyl-CoAs. But again, you can see all of these carbons and how many acetyl-CoAs you can make. Tons of them, which is why you get 9 kcals of energy from fat versus 4 from carbohydrate. Okay, so I said this, but now we have a nice picture to show it. Glycerol enters the energy pathways during glycolysis. So you can see, like, if you wanted to make glycerol, you would combine glucose with triacylglycerol, I don't think this is, oh yeah, and 3 waters to get glycerol. And then the glycerol can get broken down, and see, it's going up into whatever, not even going to say this, you don't have to memorize it, I'm never going to ask you this. But glycerol, again, bops over, and now it's part of glycolysis. So anaerobic glycolysis. We can do it without oxygen. The fatty acids have to go through beta oxidation. So these are activated fatty acids, which go into these 2-carbon, what's that good for?
Acetyl-CoA.
Yes, crushed it. In these 2 carbon groups, so plus a CoA, coenzyme A, and boom, acetyl-CoA. So they go in down here, lower on the chain. And then into the citric acid cycle, electron transport chain, yada, yada, yada. Okay. See, now aren't the pathways becoming more helpful? Are you glad I put them in? Yes. No? Yeah? Yeah, I heard a yes, thank you. I'm glad I put them in. Okay. Proteins composed of amino acids. 1 gram of protein is 4 kcals of energy, so we're back down to 4. And they contribute very little to ATP production at rest and during exercise when you're well nourished. So clearly we know about like muscle wasting and that kind of thing. When you're breaking down your protein, no bueno. We really shouldn't be using protein to create energy unless we're in an energy deprived state where for some reason we don't have enough carbohydrates and fats to satisfy it. You can see it's a pretty low energy, 4 kcals per 1 gram. So yeah, you really want to be doing off of the carbohydrates or the fats instead. What we want to use our proteins for instead, you probably know if you're trying to bulk up, use primarily as a building block for synthesizing tissue like muscle growth and development rather than ATP production. But let's say that for whatever reason you need to, your body needs to incorporate, so let's say you're in an energy deprived state, you're undergoing muscle catabolism. I believe Tyler Churchward-Vinay does research on this kind of stuff, like muscle wasting. So if you're really into this, go talk to him. So amino acids enter the metabolic pathways at different points depending on their structure. Again, please don't memorize this. Like just put a little X beside it. But I thought that once again, I can probably stop saying this, but that it helps you to understand things a little bit better. So you've got your proteins over here, made up of amino acids, and then they go through deamination, which is nitrogen removal. It's taking off amine groups. So deamination, see, even that makes sense. And then you can see, depending on what that comes up with, that's going to determine where they go in. So you can see glutamate. Have you guys ever had to memorize Krebs cycle or citric acid cycle in your class? Yeah, me too. It was unpleasant. Glutamate, is glutamate one of Krebs cycle? I'm testing you. Is it? Do you guys all forget from when you had? I saw a nod. So some of them are going straight into the citric acid cycle as, I have a list here. Okay. When you deaminate some of the amino acids, the glucogenics, because they yield pyruvate, oxaloacetate, that's what I was thinking of, or malate, which are intermediates of Krebs cycle. So you've broken down these amino acids, and they're not going into glycolysis. They're obviously not going into beta oxidation because they're not fats. They go straight into Krebs/citric acid cycle. So we're clear, you guys know those are the same things, right? I don't know why they have 2 different names. And then they can go back up through these pathways to create glucose for prolonged exercise. So again, if you're really at a point where you're, I don't know, I guess like people who are running Ironmans and stuff, I really don't know about this. You'll tell I'm not really an exercise kind of gal. But like if you're running Ironman, does everyone do like really long distance running and that kind of stuff? Oh yeah. So do you normally drink, like my friends have like those little squeezies and stuff? Yeah. And that's so that you don't start breaking down your muscle, because otherwise you'll start breaking down your muscle. Again, no bueno. So, but it'll do it because does anyone know what organ of the body exclusively uses glucose? You can't use anything else. Yeah.
The brain.
Brain. Nice. Thank you for putting up your hands. I really don't care if you put up your hands. Just yell at it next time. Yeah, the brain, which is obviously important. Okay. So now let's get into the application of all of this. So exercise intensity and duration are the most important factors that are going to govern fuel selection during exercise. And here we've got the crossover concept. So we might switch slides. Sorry if we do. No. Oh, we did. Okay, so let's start. Next point. So let's start over here. We're at 10% VO2 max, low intensity, something that even I could do. Our pink is the fats, our blue is the carbohydrates. So we're going along at like 10% VO2 max. I'm like walking into work maybe. It's so hot, man. I can't wait till it's cold and I can walk into work and not get like completely sweaty. Okay, that's another sidebar for you. So fats, we've got up here around 70% of our substrates. So we're really metabolizing a ton of fat. Which as it says here, fats are the primary fuel source during low intensity exercise. Carbohydrates, much less. We're sparing those for if. I always found exercise physiology to be useful in terms of thinking about running away from like lions or like saber-toothed tigers in our evolution. You need to have some carbohydrate fat because like you're walking into work as a caveman or whatever it is, and then you see like saber-toothed tiger, now you gotta run, so you want to have these carbohydrates stored because carbohydrates are really good for what kind of exercise? Yeah, anaerobic sprints. Because you gotta sprint away from a saber-toothed tiger exercise. Okay. So moderate intensity exercise, we're here around the 30-40% mark. And now you can see we're right about even. So equal carbohydrates and fats. And then as we get up into the really high intensity, so here we're doing, you know, sprint training, I guess just any kind of sprint. Hockey yesterday, where we really are going to metabolize a ton of carbohydrates and very little fat because we can metabolize carbohydrates much quicker without having to go through beta oxidation to make all of those acetyl-CoAs and stuff. I just said that. I'll say it again. As exercise intensity increases, the fuel mix switches, crosses over, thus the crossover concept, from primarily fat to primarily carbohydrate. And this is in line with the recruitment of type 2A and 2X muscle fibers, which are the fast glycolytic muscle fibers that support high power. And also increased, those both say one, sorry, increased neurohumoral activation with increased release of epinephrine, norepinephrine, and glucagon, and decreased release of insulin to stimulate muscle and liver glycogenolysis. Epinephrine, this is sort of like my jam, the epinephrine, norepinephrine. I do a lot of autonomic stuff. And whenever you do exercise, you get a massive increase in sympathetic outflow, which is going to result in a lot of release in epinephrine and norepinephrine. So even mental stress. So you're walking along as a caveman, you look over, that's probably a bad example because they're not Homo sapiens, right? Anyway, so you're walking along as a Homo sapien, you see a saber-toothed tiger, and automatically your body's like, oh God, so you have a huge sympathetic response, the fight or flight response. So a huge increase in epinephrine and norepinephrine, which is going to stimulate your muscle and your liver to break down glycogenolysis, breaking down glycogen, create glucose so that you're ready to go and do your sprints away from the saber-toothed tiger. Is my saber-toothed tiger example working for you guys? Okay. Okay. So is low intensity exercise best for burning fat? So low intensity exercise at 20% of VO2 max, you get about 60% of your energy from fat. So you can see at that 20% mark, we've got that fat, which is the pink. 60% of the energy is coming from fat. But at 80% of VO2 max, 20% of it is coming from fat. So let's say you're really keen, I decide like, I'm gonna burn off my fat. How should I be exercising? I'm going to warn you, I'm tricking you here. All right, I'll leave it because I just told you I was trying to trick you. So if you burn 250 calories after 1 hour of exercise and you consume 150 calories from fat oxidation. So again, we'll follow this 20% up. So this is me, I don't know, doing like a easy jog on a treadmill. 60% of my energy is coming from fat. rate, burning fat. I'm burning 250 calories an hour because it's not like a super intense exercise. So I burnt 150 calories from fat because of 250 times 0.6. Now the thing about high intensity exercise is it's high intensity and it's hard to do, and it burns a lot more energy. This is where I was tricking you. So let's say you're up at 80% VO2 max. So this is me like dying on the treadmill right before I puke. If we burn 850 calories in an hour, I would never last for an hour at that rate, but anyway. Then if we do that math, 850 times 0.2, we still burn 150, or we still get 170 calories from the fat oxidation. So this is where the whole burning fat at a low exercise intensity kind of falls apart. Sure, you're getting more of your energy from fat, relatively speaking, but you're burning less calories. So that's why you're getting less fat use. Does that make sense? Which is why I do high intensity interval training when I exercise. The big caveat there. Okay. So the absolute, this is just what I just said, the absolute amount of energy derived from fat is greater during moderate to high intensity exercise versus low intensity exercise, even though the relative amount of energy derived from fat is lower during moderate intensity versus low. So a very nice figure over here showing exercising at 20, 50, 80, and 100, and the kcals that you're burning from fat per hour. So here's your sweet spot up here at the 50. So before the crossover effect has really brought your fat way, way down relative to carbohydrate, but it's intense enough that you're burning quite a few calories. There's sort of your sweet spot for the fat oxidation. Cool. Some confused faces, but it's all right. Does anyone need me to re-explain or go back? I'm going to keep going. Okay. During prolonged low-intensity exercise lasting more than 30 minutes, there's a gradual shift from carbohydrate metabolism towards an increasing reliance on fat oxidation. So this time across the x-axis there, we're not increasing exercise intensity. Now we're just exercising for longer. So I choose to wander around Montreal for the day, give my tours and stuff like that, but walk it in a fair click. So we're doing like a nice low intensity prolonged exercise. So remember on our previous slide, we can say, okay, we're going to be here on the curve and we're just going to be burning, let's say 60% fat, 30% carbohydrate. It's not actually how it pans out, because over time you're going to increase your reliance on fat and decrease your reliance on carbohydrates. Fat metabolism depends on the factors governing lipolysis, particularly the activity of lipase enzymes, which remember we said those are things breaking down that triacyl, why can't I say that? Triacylglycerol? Yeah, thanks guys. Am I saying it wrong? Okay, good. Into the glycerol and the free fatty acids. So those enzymes are going to really control the rate at which we do fat metabolism. So they're generally inactive until stimulated by increased circulating levels of norepinephrine, epinephrine, and glucagon, again, which are going to happen when you're sort of stimulating your sympathetic nervous system. You're under fight or flight conditions. So just get really stressed out all the time is what I'm taking away from this. So during prolonged low-intensity exercise, progressive increases in neurohumoral, I can't say that, activation, you get it, of the sympathetic nervous system, which is what I just said, results in progressive activation of lipase enzymes and thus lipolysis. A little redundancy on that slide for you. Okay, so what about the impact of exercise intensity? So that's if you pick an intensity, a nice low intensity, and you go with it. Percent fat's going up, percent carbohydrates going down. So this is actually a really nice figure that shows, oh no, I pressed too many. Okay. The different exercise intensities across the x-axis here, and then the percent of total fuel source across the y here. It's kind of bright. You guys can see it. You've got laptops. I'm done. When I was in undergrad, we all printed off our slides in black and white and wrote on them. It was quite some time ago. It was like one kid in class that had a laptop every time. Does anyone print off their notes? No, eh? Yeah!
I'm 40 years old.
Yeah! Nice. Okay, good. It's so hard to break us of our habits, but this is nice because you all can see color. Okay, so I've got muscle glycogen in the teal, plasma glucose in the pink, So those are your carbohydrates, obviously, and then the plasma-free fatty acids in that nice taupe color, and fat in purple, I guess. So you can see the carbohydrates are really, it's sort of just another way of showing you the figure that I showed you before with the crossover. Why can't I? Okay, okay, so carbohydrates are obviously like, they're here, and then they're here at the 65, and then they're here at the 85, which we've covered. High intensity exercise, you're using carbohydrates as your energy source. Fats vice versa, crossover. So here we're highlighting the plasma glucose in the pink. Blood glucose plays a relatively greater role than muscle glycogen during low intensity exercise. So the teal is our muscle glycogen, and here's our plasma glucose. And low intensity exercise, we're saving that muscle glycogen for when we really need it, which is up here at these high intensities, and relying on the plasma glucose. And the muscle glycogen plays a relatively greater role than blood glucose during high intensity exercise. So again, we're repeating ourselves over and over here. Increased rate of glycogenolysis due to recruitment of type 2A and type 2X muscle fibers, increased neural humoral activation of glycogenolysis. These are all really hard words to say. With increased release of epinephrine, norepinephrine, and glucagon. And then plasma-free fatty acids play a relatively greater role than the muscle triacylglycerol. I made up a new word. Energy supplied via fat metabolism during low-intensity exercise. And then as you go up, you start dipping into those muscle stores. So I think a nice way of sort of I was going to say memorizing, but understanding this is when you're at these low intensities, like think of my saber-toothed tiger that like you're walking along, you want to be saving those muscle stores are real handy. They're there really fast for you. They're at the muscle. You don't have to transport things from the liver. You're ready to go. So it makes sense that we don't use muscle glycogen when we're at these low intensities of exercise. The high intensities are the ones that are going to like keep you alive from the saber-toothed tiger. So it makes sense that the plasma glucose is basically staying roughly the same, but the muscle glycogen is taking over as you go up to higher intensities. The plasma-free fatty acids, just circulating in the bloodstream, we're going to use more of them when we're at low intensities, and that number is going to go down, and we're going to use the muscle triglycerides, particularly at those moderate intensities. Okay, what about the impact of exercise duration on fuel selection? So we touched on this a little bit already. It's a fun y-axis to read. So percent of energy derived from the four major fuel sources during prolonged submax exercise. So we're looking at 65 to 75%. Yeah, sorry, I said to do the same thing. VO2 max. So again, now we're up at, not again, now, before I was talking about low intensity exercise prolonged, now we're at like a fairly moderate to high intensity exercise. And we're going to sustain this for 4 hours. This like sounds intense. So we start off, as we saw in that previous slide, with muscle triglycerides and plasma-free fatty acids and muscle glycogen being our dominant sources. Shall I go back? We're looking right between here and here, basically. So at the beginning of prolonged submax exercise, we have plasma-free fatty acids and intramuscular triglycerides contributing equally to fat metabolism. But as the exercise time increases, there's an increased reliance on plasma-free fatty acids to fat metabolism. And those are getting released from your fat cells. What's the right word for those? Thank you. Thank you. I shouldn't have asked these guys. Ask you guys. Okay. Through lipolysis. Yeah.
Since like we're using more blood glucose towards the end, does that assume that like you're drinking sugary drinks like throughout?
I think it's assuming that you're harvesting, you're creating glucose at the liver. So the liver's got all those glycogen stores, and so they're dumping them into the bloodstream. Yeah. I think this is probably assuming, my guess, this is assuming that you're not doing any of that sipping. So the idea behind the sipping is to sort of keep that at bay and not break down your like liver glycogen and your muscle glycogen as much as possible. If you're like, hey body, look, here's more plasma glucose, like use this instead. And then you can save all of that for the end when you really need it. Or keep going even longer than 4 hours.
So when it says muscle glycogen, does that also include like liver glycogen, which then transfers off?
I think you're getting
to the
your blood glucose from the liver glycogen.
Okay.
Yeah. Okay, so during the first hour of submax prolonged exercise, the majority of carbohydrates comes from muscle glycogen. However, as time increases and muscle glycogen content gets depleted, blood glucose becomes more and more important source of carbohydrate metabolism. Again, all coming from your liver stores. This is a fun title. This is a dentist slide. Fats burn in the flame of carbohydrate. It's good stuff. Okay, so during prolonged, like greater than 2 hours of submax exercise, your muscle and liver glycogen stores become depleted. This might answer your question right here. So glycogen depletion decreases glycolytic flux and the rate of pyruvate production. Dennis had this slide up, so now you can't blame me for all of these pathway slides. This is actually a beautiful slide because it shows everything all together. Actually, it doesn't show glycogen, which is why he has his arrow there. So remember, glycogen comes in at, does anyone remember where glycogen comes in? If you were thinking glucose 6-phosphate, you were right. Okay, so we've got glycogen pumping itself into glycolysis, but glycogen depletion decreases glycolytic flux and the rate of pyruvate production. Again, why you want to be sipping those little, what even are they? Just sugar, I guess, simple sugar? Yeah. Are they pleasant?
No.
No, yeah, it seems unpleasant. Especially while you're running. Okay. This is kind of what I was saying earlier, but pyruvate contributes to the rate of oxidative phosphorylation by providing Krebs cycle intermediates. This is actually, I think, exactly what I was saying on the previous, well, near the beginning. And as the rate of glycolysis and pyruvate production decreases, the concentration of Krebs cycle intermediates decreases, and then the rate of oxidative phosphorylation decreases. So glycogen depletion, bad.